Hi everyone. Hello, hello. Hi everyone. Am I audible? Is anyone there? Let me know. Hello everyone. Okay. So let's start. Hi everyone. My name is Pradyumn, and today we will discuss the solutions for A to E for today's educational CF round. But before we start, I'll tell about the courses at TLE Eliminators. So if you're someone who is stuck at just solving one or two rows per contest, then these courses are what you need. Okay. So as you can see here, we have these courses which are divided into four levels. So you can start from wherever you are right now. Either you are a beginner, or you are pre-intermediate, or you're intermediate, or advanced. So you can start from wherever you are, and you will learn the most relevant CP concepts through video lectures, and followed by practice problems which have guided hints and video solutions that help you understand the why and not just the how. We believe in helping you build real intuition. And if you need more help, you will get instant doubt support from our top rated mentors, so you are never left stuck. And beyond just learning, you will enjoy leaderboards, progress tracking, internal contests, and PCDs to keep you consistent. Pick the level that fits your goals and start learning today. And if you're confused that which level you should choose, then you can watch this video. Okay. And if you're still not sure, then you can go to the level and watch that video, which will tell you about the course and what are the prerequisites, outcome, difficulty, and topics. All right. So you can look at this. So let's start now with the PCD. Uh, okay. So this was today's contest. The first problem was New Year string. We will call a string consisting of characters 0, 2, 5, and 6 a New Year string if at least one of the two conditions is met. It contains the string 2026, or it doesn't contain the string 2025. For example, the strings 2025, 2026, this is good, like a New Year string, and 21026, it is a New Year string because 2025 is not there. Okay. Given a string S, you can perform the operation any number of times. So choose a character in the string and replace it with 0, 2, 5, or 6. Okay. So you need to calculate the minimum number of operations needed to make the string S a New Year string. Okay. So like what we have here is a problem which says that you have a string containing 2, 0, 5, and 6. Okay. And you have to determine, like, okay, what they are saying is a string S is nice, like it is good if either it has either it has a 2056 in it, I mean sorry, 2026 in it, or it doesn't have a 2025, right? So if any one of these two conditions is met, then this S is good, right? And what you can do is, given the string S, you have been given a string S, and you can change any character and to anything, like to any of these four characters, and you have to ensure that the string is no longer good. I mean sorry, you have to make the string good, right? So what is the minimum number of operations that you need to do? Okay. So for example, we have this string right here, 2025, 2025, right? So actually we can change this 5 to a 6. Okay, right now it is not good, right? It's not good because it doesn't have 2026 also, and it has 2025, so it is not good, right? So what we can do is we can change this 5 to a 6. So now the string becomes 2026, 2025, and now it is good because it has a 2026. So even though this has 2025 also, but we don't care about it, because it has 2026, so this is satisfied, right? We just have to satisfy any one of the conditions. Like either it should not have 2025 or it should have 2026. So we need only one condition to be satisfied, at least one, right? So this string is good. Um, so what is the solution? Like first of all, if the string is already good, if it is already good, so the answer is zero, right? The answer is zero. Okay. But what if it is not good already? Then how do you make it good? That's the question. So if a string is not good, if a string is not good, then what it means is that both of these conditions are false, right? One is false and two is also false, right? That is, if a string s is not good, then it does not have 2026, doesn't have 2026, and secondly, it has a 2025, right? Therefore, it is not good. So, if you want to make it good, you can actually simply change this 2025 to the 2026. Like, just change this 5 to a 6. Like, the string s, the string s has a 2025, right? So, you can simply change that. You can simply change this 5 wherever it comes to a 6, and it will have a 2026 then. So, condition 1 would satisfy. This condition 1 would satisfy, and the string s would become good, right? So, if the string is already good, if it is already good, then answer is 0. And if it is not good, then there is a 2025 in the string, and you can make it a 2026 in one operation. So the answer is 1. Okay. So this was pretty simple. Just the implementation is um, a bit long, but yeah, PNC based. Not like, I guess, D only, and D also was not very tough. Okay. So A was easy. So I'll show the code also for A. It's trying to load. Like in the code, I use s dot find function. Like you have in the C++, a string has a find function, right? Like std string has a function called find, where you can give a string s dot find, and you can give a string like either a character here or a string as well. Like if I say s dot find 2025, then it will search for that substring inside the string s and return the position where it found it. And otherwise, it will return npos. Like npos is a variable which is declared inside the header, so it will return npos if it does not find the occurrence, and if it does find it, then it will return the index of the first letter. Okay, so I can just use this function to check if the string is good or not. Like to be for it to be already good, the string has to have either 2026, or it does not have to have 2025. Okay, so yeah, um, the code is not okay. So here we have solve function में int and c in string s c in s, if s dot find 2025 is not equal to npos string colon colon npos, then okay, so basically it has 2025, right? The string has 2025. So if it also has 2026, then the answer is 0. Otherwise the answer is 1. And if the string does not have 2025, then the answer is also 0, right? So this is the solution. All right, so I think it should be clear. I'll move on to the next one. So the next problem was New Year cake. Monocarp is going to bake a New Year cake. The cake must consist of at least one layer. The size of the top layer of the cake must be 1. Size of bottom layer must be 2. Like the layer below it must be 2. The size of layer below it must be 4, and so on. So each layer is double the size of its top layer. Additionally, each layer must be covered with either white or dark chocolate. And to cover a layer of size K, monocard will need K kilograms of chocolate. Each layer must be covered with exactly one type of chocolate, and these types must be alternate. Okay. Monocarp has A kilograms of chocolate, of white chocolate, and B kilograms of dark chocolate. He wants to calculate the maximum number of layers that he can make. Okay. So this is also a problem which is not very hard. So like what they are saying is I have a cake, right? And the cake consists of layers. So the top layer is of size 1, then the layer below it of size 2, then the layer below it is of size 4, and so on, right? And what I have to do is either it should be like black, white, black. So I will, what should I do? Let's say this red is dark chocolate and white is white chocolate. Okay. So either it has to be like black, white, black, then white, and so on, right? Or it has to be like white, black, white, black. So first layer is of size 1, which is white. Then it has to be a black layer of size 2. Then it has to be of size 4, a white layer, and so on. So either this or this, right? There are only two cases. And one more thing is that the size of these layers, the size of these layers is growing exponentially, right? Like the first layer of size 1, second of size 2, third of size 4, fourth of size 8. So like it won't be very much long time until we reach a size which is very large, like 2 to the, like basically in the problem the constraints are that A and B, A and B, like we have A kilograms of white chocolate and B of dark chocolate, right? So the limit on A and B is up to 10 to the power 6 only. So like at max we will have 10 to the power 6 kgs of chocolate. I mean, I wish I had this much chocolate, but okay. So we had basically we have at most this much chocolate. So this cake is growing so fast that like 1, 2, 4, 8, 16, 32. So it won't be very much time until we reach 10 to the power 6. In fact, like 2 to the power 20, if you see, it's already greater than 10 to the power 6, right? So if the cake just has 21 layers, then also it is not possible. Like if your cake has 21 layers, then the last layer would be of size 2 to the power 20, right? And that is not possible to be because 10 to the power 6 is the limit of our input, right? So definitely our answer is less than 21. Okay, that is the main observation here, that the layer size is growing exponentially. So you can kind of do a brute force because the maximum possible answer is 20, right? Maximum answer is 20. So like you can try to build the cake one by one. Like let's say we have only two cases, right? We have only this case and we have this case. So we can try both the cases and just print the answer which is larger. Okay. Like let's say we have um, in the input 5 comma 2. Okay. So I have 5 kgs of black chocolate, 5 of white, and 2 of dark chocolate, right? So first I'll try that. Okay, let's start with white. So if I start with white, so 1 kg of white, okay, and 0 of black. Then in the next layer 0 of white and 2 of black. Then in the next layer 4 of white and 0 of black, right? Then in the next layer I would have tried that 0 and 8, but since this black is not enough right now, like I have only 2 kgs of black chocolate and I need 8, so this is not valid. So the answer would be 3 if I start with white. If I start with white, then the answer is 3. And now let's try to start with black. Okay. So if I start with black, 5 comma 2. If I start with black, so it will be 0 1 on the first layer. Then it would be 2 comma 0. Then it would have been 0 comma 4. but I don't have enough chocolate here. I don't have a 4, so I will stop here. And the answer is 2 if I start with black. So the maximum of 3 comma 2 I will print. Maximum of 3 comma 2. Right. So this is how you can just do it. Like iterate from 1 to 20. And as soon as your chocolate gets finished, just break. And that's your one of the possible answers. And you have to so basically it will take 20 steps to find the answer, or like 40 steps, because you have to do it 2 times. So 40 into t, that is the complexity of this test case, complexity of this um, like solution, right? So do you guys understand B? If a is greater than b, then swap a b and then solve. um like it's because it is the power of 2, right? Like if you see, for any cake that I build, like let's say if I start with white, if I start with white, so 1 comma 0, then 0 comma 2, 4 comma 0. Okay, I mean that should not work. It's working. Like what I understand you are saying is that that should not work actually. Why it should not work? Like if you are saying that if a is greater than equal to b, then we swap ab, right? So basically a is less than equal to b, right? So like if you want to solve it, let's say the test case is, okay, for this test case, like if we have 5 comma 2, right? Then if you swap a and b, so you will get 2 comma 5. So you are saying that start from white, right? So if I start from white always, then this is working, this test case. But let's say um, the test case is 2 comma 1. Okay, 2 comma 1 is, okay, you are saying start from black, right? Like in your solution, what I understand is you are saying that if a is greater than equal to b, then swap a and b, and then start from black. Start from black, right? So if you do that, then it would not work for this test case, right? Like 1 comma 2. So if you start from black here, then it would be 0 1, and then you cannot put a 2 0 here because it doesn't work. And let's say if you are saying that start from white, then this not like, then 5 comma 2 does not work. Like you will swap it for 2 comma 5, and then you will say that start from white, so you will say 1 0, then 0 2, and then you cannot do a 4 0, right? So wrong answer. So like it doesn't work. Why are you saying it works? Yeah, exactly, that's what I'm doing. See, the Jiangli's code. Okay. I think Sarafat Hussain does not um, like Zaid Khan is saying something else and Sarafat is saying something else. Like Sarafat, you are saying that just calculate the answer for AB, then swap them and again calculate the AB and then print the maximum. You are saying that, right? But Zaid, like what Zaid said is that if A is less than B, then swap and then just print that answer. It's not opening, but I told you why it wouldn't work. Okay, it worked. It is opening. Yeah, so he's not doing that. He's doing something else entirely. Okay, he's not doing that. So what I am doing, he is not doing. Like if in my code, like if I show you my code, um, yeah, here it is. If I show you my code, then what I am doing here is not the same as what he is doing. Okay, wait. Yeah, so here is my code. It's pretty long for B, but okay. All right. So in my code, what I'm doing is um, int AB. Yeah. So I have int AB C in AB, answer equal to 0. So I'll store the maximum in this. Then the first check is for like if I start with a black. Okay. So I just loop from I to from I is equal to 0 to 30. So if I is odd, then I'm adding it to C. So C is the amount of white that I used, and D is the amount of black that I used. Okay. So if C plus 2 to the power I is less than equal to A, then I'll add it. Otherwise, the answer is equal to max of ans comma I and then break. Okay. And if I is even, then I'll add it to black, the dark chocolate, right? And in the second test, like second case, what I did was I did the reverse. Like here I'm checking if it is odd, then I will add it to my white chocolate. And here I am the same code, but I am checking if it's even. So if it is even, then I will add it to my white chocolate. Otherwise, I'll add it to my dark chocolate. Okay. So if in this code, if in this code I don't do this, and instead I just do if A greater than B, swap AB, then this won't work. That is my point. But what Gianni did is something else. I won't go into that, like what he did, but this is my point. Yeah. So that's what I'm doing, right, Sarafat? Anyways, is the code clear? Use GPT. Why do you think so? Like, I won't make any comments on that. I mean, the code looks pretty. Like, I don't think we use GPT. Why do you think? All right, let's go to C now. Production of snowmen. To create a truly festive atmosphere, Santa's helpers have opened a factory for producing snowmen. Each snowman consists of three snowballs, a head, a torso, and a legs. For snowman to be stable, the ball forming the legs must be larger than the ball forming torso, and in turn, the ball forming the torso must be larger than ball forming the head. Formally, if we denote the size of the head, torso, and legs as ABC, then the snowman will be stable if A is less than B less than C. At the snowman production factory, there are three conveyors, each containing n snowballs. First conveyor contains balls of sizes A1 into up to AN. Second contains sizes B1 into up to BN. And third contains sizes C1 into up to CN. Converse are cyclic. In other words, after the element is numbered n, the element numbered 1 again follows. And we can consider that the ball numbered I and I plus n are same. To produce Snowman, it is necessary to specify three parameters I, j, and k, indicating which balls on each conveyor of the production starts from. After that, the snowman are assembled from the like balls as follows. The first snowman has a head of AI, torso of BJ, and legs of CK. Second snowman will have a head of size AI plus 1, torso of size BJ plus 1, and legs of size CK plus 1, and so on. And then the last snowman will have a size of A of I plus n minus 1, BJ plus n minus 1, and CK plus n minus 1. So we have to choose the parameters in such a way that all the n snowmen are stable. Our task is to calculate the number of suitable combination of parameters. Okay. So like we have the problem that basically there are n arrays. Like n cases. We have three arrays. Let's take a test case. Let's say we have this case 1 4 2 3 5 1 4 2 3 5 6 4 5 7 6 and 7 5 8 10 10. Okay. And we have to basically, like, what will happen is we can choose three indices. Let's say in the third example. Okay, they haven't given fourth example. All right, so let's say we choose this index for the first array, then this one for second array, and this one for the third array. Okay, so what will happen is um, the snowman will start building. So the first snowman would have these three. Okay, so he will have 2, 4, and 10. Okay, then second snowman will have these three, 3, 5, and 10. 3, 5, and 10. Then the third snowman would have this one, and this one. Like here, it is adding, right? So cyclically, we go back. So these three, that is 5, 7, and 7. Then fourth snowman would have this, and this. So 1, 6, and 5. And fifth snowman would be 4, 6, and 8. 4, 6, and 8. Right. So you can see that these five snowmen have formed, but they are not stable. Like this one and this one are not stable because um, this A less than B less than C is not satisfied. Right. So the indices that we chose, like we chose this one, right? We chose index I equal to 3. Like if I write 1, 2, 3, 4, 5 here, we chose I equal to 3, J equal to 2, and K equal to 4. So this 3 2 4 is not a valid pair. Okay. So we have to choose like a valid pair. We have to count the number of valid, like not pair, sorry. This is triplet. So we have to count the number of valid triplets. Okay, that is the problem. That's the question. And someone said I don't understand the question, so do you get it now? Someone said that I did not understand C. Yeah, they said that I can't understand the C problem. So do you get the problem now? Like I hope you do. Okay. So what we have here is the like we have to count the number of triplets, valid triplets I, J, K, which satisfy the conditions, right? So what is the most brute force that you can think of? Like what is the most brute approach? Like let's say if I just iterate over all I, J, K, like for I equal to 0 to n minus 1, for int j equal to 0 to n minus 1, and k equal to 0 to n minus 1. And if you just check if this ijk is valid or not, so you will check ijk, and if it is valid, then you will add 1 to your answer. So like ans plus plus. Otherwise, you don't do anything to the answer. Otherwise, 0, right? So if you do this, then how much will it, like, what is the complexity of this? So it is O of n to the power 4. Why? Because this check function will take O of n, right? Like if I want to check that is a valid index ijk, like is an index ijk, let's say 3, 2, and 4, 3, 2, and 4, if it is valid or not. So I will need to check O of n. Like first I will check these three elements, this one, and this one. Then I will check these three elements, right? Then I will check these three elements. So I will like stop as soon as I find something that either a greater than equal to b or b greater than equal to c. If I find this, then I will return false, right? But it will take O of n in the worst case. Okay, so this check function is taking O of n, and so if we have three for loops here, and we have one O of n loop, like O of n function. So it would be O of n to the power 4, right? And it is too slow because the constraint on n is that it is still 5000. So 5000 to the power 4 will not work. And in fact, for 5000, only n square will work. Okay, even n cube won't work. So we have to like optimize this approach to O of n square. Okay. So n to the power 4 को n square करना है. So how do we do that? Now, first thing that you can notice is that we have a symmetry here. Okay. Like let's say if I have something in, I'll take that test case only. Okay, I will copy it from here. Yeah, so um, we have this, right? So let's say, what is one correct answer in this? Can you guys tell me? Like I think maybe this 4 would work with this 5 and with this 2. It works. Does it work? Yeah, so this index, that is uh, basically if I index this 0, 1, 2, 3, 4. So the pair 2 comma 1 comma 1, it works, right? Why it works? Like the first is 2, 4, 5, then it is 3, 5, 8, then it's 5, 7, 10, then it is 1, 6, and 10, and then it is 4, 6, 7. So all of these 5 snowmen, they are stable, right? So this 2, 1, 1 works. Okay, so my point is that you know that 2, 1, 1 works. So actually you also know that 3, 2, 2, 3, 2, 2 also works. Why? Because 2, 1, 1 starts from here, right? But 3, 2, 2 starts from here. Like it is the same thing. See, 2, 1, 1 is same as 3, 2, 2. Why? Because 2, 1, 1 will have this one, this one, this one, this one, and this one. But 3, 2, 2 also have the same 5. 3, 2, 2 also has this one, this one, this one, this one, and this one. But this thing is that 3, 2, 2 starts from this 3 instead of the 2, right? But it has the all the same 5 snowmen. So like 2, 1, 1 has the same 5 snowmen as 3, 2, 2, right? So if 2, 1, 1 is valid, then this is also valid. Okay. So basically, if you have a valid pair ABC, then actually you can shift it by anything. You can do A plus K, B plus K, and C plus K. Okay. And this is also valid. Also valid. So actually what you can do with this information is that you can fix one of the indices. Like you can simply basically just fix I equal to 1. or I equal to 0, let's say. Like you will always start from here. So instead of counting ijk, what you can count is 1 comma j comma k pairs. 1 j k, right? And then you can like get the answer from this, and you will simply multiply it by n. Like you will simply multiply the answer by n, because whatever valid pairs of j comma k you get, you can simply shift them n times. Like either you can have 1 here, or you can have 2 here and j plus 1 and k plus 1, and 3 j plus 2 k plus 2, and so on. So you can have n different shifts of the same answer. So the final answer would be ans into n, right? So this for loop of I equal to this first for loop, it is useless. Okay. So now our complexity is n to the power 3, O of n cube, right? That is okay, but we have to take it to n square also, right? So did you understand this first one, that how we came to O of n cube? Like why is this first for loop not needed? Did you guys get this, why it is not needed? X Cali draw. Okay, I'll note that. I'll try to I'll try it, and next time maybe I'll use that. Okay. Once more. So what I'm saying is that I'll take this one only. We have this example, right? Or okay, wait. I will space this out a little more. Yeah, this is the example. So what I'm saying is, let's say we have a valid pair 2, 4, and 5, right? Like basically this I is equal to 3, j, or let's take it 0 indexed. Okay, so 0, 1, 2, 3, and 4, they're the indices. Okay, so what I'm saying is 2 comma 1 comma 1, like I2, J1, and K1. That is, if I start from these three indices, then it is one correct answer. This is a valid answer. And why is that? Because all of these snowmen that I build, that is this 2, 4, 5, 2, 4, 5, then this 3, 5, 8, then this 5, 7, 10, then this 1, 6, and 10. Okay, I'll write them for you. Okay, 2, 4, 5, 3, 5, 8, 5, 7, 10, 1, 6, 10, and 4, 6, 7. Right? So these are the five snowmen that you will be getting, right? Okay. These five you will be getting 2, 4, 5, 3, 5, 5, 7, 10, 1, 6, 10, and 4, 6, 7. Right? And you can see that all of these five are stable. All are stable. Right? So you can say that this 211 is valid. Okay. So what I am saying is that if you shift this 211, like if you shift all of the indices by some number, let's say if you add 1 to all of these, like 2 का 3 कर दिया, 2 plus 1 3, 1 plus 1 2, and 1 plus 1 2. If you change this 211 to 3 to 2, then what happens? Then basically your first index is this one, this one, and this one. So you will get 358 as your first snowman. Then you will get 5710. So you will get 5710. Then you will get 6101, right? Then you will get, I mean, sorry, 1610. Then you will get 467, which is here, and then you will get 245 in the end. So like if you start from 322 instead of 211, then you get the same snowman, right? You get the same 5 snowmen which you got earlier. but just in different order, right? So if you're initially all the snowmen were stable, then of course even if you got them in different order, then also they will be stable. They would be stable, right? That's my point. That if you know that the indices I comma j comma k, this is a valid index, then you also know that if I add some number l to this, I plus l, j plus l, and k plus l, then this is also valid because we will get the same snowman using this, right? So actually, what I can do is I can simply count the number of valid pairs. Like I can fix I to be one. I can simply put I is equal to one, and I can just count the number of valid pairs I 1 comma j comma k. Right? Like initially I was iterating over I j k, but now I will fix I to be one, and I will count the pairs 1 comma j comma k. So let's say I got three pairs. Okay, I got 1 1 2, then I got 1 3 1, and let's say I got 1 3 2. So let's say these three pairs were the correct answer. Okay. So now how do I get the other pairs? Like let's say n is equal to 3. Okay. If n is 3 and I got these three pairs, right? Then actually I can shift them by 1. Like, okay, these three are the answers. Then if I shift them by 1, then I will get, uh, like if I shift them by 1, then I'll get all of the answers with I equal to 2, right? So 2, 2, 3. Then I will get 2. This 3 becomes 1, right? Because n is 3. So again, cyclically it goes back. So 2 1 2 and 2 1 3. So if I shift them by 1, then I'll get these three triplets, and they are also valid. And if I shift by 2, then I will get all of the I equal to 3. So I'll get 3 3 and 1. Then I will get 3 2 3, and also I will get 3 2 1, right? So these 9 triplets I have. If I shift by once more, then I'll get the same back here, right? So for I equal to 1, if I get 3 triplets, this is for I equal to 1. Then for I equal to 2 also, I'll get 3 triplets, and for I equal to 3 also, I'll get 3 triplets. So I can just count for I equal to 1. Answer I will count for I equal to 1, okay, and I will just multiply it by n. So I'll do ans into n, and this is the final answer. Okay. So whoever told me to do it once more, do you guys get it now? Understood? Okay. So yeah, so that's how we can get like from n square or n to the power 4 to n cube, right? But now what else do I do? Like it is still n cube, right? I need to make it n square. So right now what we are doing is we are checking um like we are checking the all the pairs 1 comma j comma k, and we are doing the check. Like we are calling check function for all 1 comma j comma k, right? But how do I make it more efficient? So basically what we are checking is like basically the condition that we are checking is that my ai should be less than bj, should be less than ck, right? Like my ai should be less than bj, should be less than ck. This is the condition that we are checking, right? That is, um, if I'm checking for ijk, let's say if I call the function for ijk, then first I'll check that ai less than bj less than ck, or like, and also I will check that a of I plus 1 should be less than b of j plus 1 should be less than c of k plus 1, right? Then also I'll check that a of I plus 2 is less than b of I plus 2 and c of I plus 2, and so on. Like I will check for all the indices like this. if I am checking for ijk, right? So the entire point is that I am checking a less than b less than c, right? So actually, you can see that these two are not interacting with each other. Like this A and C, they are actually independent. Kind of. Just think of it like that. That this A and C, they are independent. Like if I count B less than C, and if I count A greater like B greater than A, then automatically A less than C is already there. Like if I have three numbers such that B is less than C, and also I know that A is less than B, right? So automatically A less than B less than C is satisfied, right? So my point is that I only need to say ensure that B less than C and A less than B. Like I don't have any relation between A and C. Like I don't really care about A and C. Okay. So like see my point is, let's say I have these three arrays A1, A2, A3 to A5, A4, A5. Okay. And same for B and same for C. I have these three arrays C1, C2 and so on. So now if I know that um, for these two arrays, like let's say that I know that here j is like ijk, right? So if I know that j equal to 2 and k equal to 3 is valid, like let's say that I know that j equal to 2 and k equal to 3 is valid, that is I know that b of 2 is less than c of 3, then b of 4 is less than c of, sorry, b of 3 is less than c4. Like just look at b and c right now. Okay, so b1, b2, b3, b4, b5, and c1, c2, c3, c4, and c5. So if I know that b2 is less than c3, b3 is less than c4, b4 is less than c5, b5 is less than c1, and b1 is less than c2. If I know these five things, then I will call that this j2 and k3 is valid. Okay, like I can possibly use that with some I equal to something. Okay, like if any of these is not satisfied, like let's say if b1 is greater than b1 is less than c2, okay, then it is not valid. So then this 2 comma 3 pair is not valid, right? So we can never have it in the answer. But if this 2 comma 3 is valid, then we might possibly have some I for which you can have that in the answer. So which I will it be? So all the i's for which, like let's say if I want to check that is 1 comma 2 comma 3 valid, so actually I can just check that is 1 comma 2 valid. Like if 1 comma 2 is valid and 2 comma 3 is valid, j is equal to 2 and k equal to 3, if this is valid, if both are valid, then actually I can say that 1 comma 2 comma 3 is valid. Okay, like my entire point is that for a less than b less than c, if you fix a b, then my c has to be greater than b and a has to be less than b, and so they are independent. So we can simply count all the tuples with satisfy b less than c and will satisfy a less than b, and we can combine them, like multiply them. Okay, like I will show you on the test case. I'll show on this one only. Okay, let us copy this. So we have this a, b, and c. I will index this 0, 1, 2, 3, 4. and here I have A, B, and C. So first I will count that for A and B. For A and B, what pairs I can choose. Okay. So actually you can see that all the elements here. Okay, no, sorry, my bad. So I will count. Okay. So does A equal to 1 and B equal to 1 work? So actually, okay, let's say if I'm only seeing these two, okay, then there are only five possible combinations, right? Like I either I start from 1 1, or from 1 2, or from 1 3, or from 1 4, or from 1 5, right? Because 1 1 is same as 2 2. So actually, instead of 25 combinations, I only have five essentially, right? So if I'll check all the five, first I'll check this. First I'll check this one. Okay. So since this 4 is not less than 4, 1 1 is not valid. Okay. So then I'll check 1 2. So 4 less than 4, 4 less than 5, 2 less than 7, 3 less than 6, and 5 less than 6. So 1 comma 2 is valid, right? Then 1 comma 5. So 1 5 4 7 2 6 3 6 5 4. So we have this 5 4. So 5 4 is not good. Okay. Then 1 comma 4. So 1 7 4 6 2 6 3 4 and 5 5. 5 5 is not good. And let's try for 1 6 now. So 4 6 2 4 3 5 5 7 and 1 6. So this is also valid. Like A1 and B5, this is also valid, right? And now if I count for this B and C. So actually in B and C you can see that all the elements of B are less than all the elements of C, right? So actually all pairs satisfy. So if you see B and C, so 1 comma 1 satisfies, 1 comma 2 satisfies, 1 comma 3 also satisfies, 1 comma 4 also satisfies, and 1 comma 5 satisfies, right? So these five pairs I have for B comma C, and for A comma B I have these two pairs which satisfy, right? So now for A comma B comma C, I effectively will have their product, that is 10 pairs actually. Or oh wait, what I'm saying, I'm wrong, my bad guys, it is not true. Yeah, so what I'm saying is for A comma B we got two pairs, right? And similarly we'll count for B comma C. So I'll count 1 1. So is 1 1 working? 6 7 4 5 5 8 7 10 16. Okay, 1 1 is working. Then I'll count 6 5. So 6 5 it is not working here itself. Then I'll count this. So 6 8 4 10 5 10 7 7. We have 7 7. No, it doesn't work. Then 6 10. So 6 10 4 10 5 7 7 5. 7 5 doesn't work. And then we will look at this one, 610. So 610 4755 doesn't work. So for this B and C, we have only a single pair which works, right? So for A and B we have two pairs, and for B and C we have one pair. And actually to combine them, let's say I shift this, like 1 comma 2 is same as what? It is same as 5 comma 1. Like what I am saying is, if 1 comma 2 is valid, then like I can shift this, right? Let's make B equal to 1. So 5 comma 1 is valid. Okay. And 1 comma 5 is same as uh, okay, wait. Yeah, 1 comma 5 is same as 2 comma 1. Like if I add 1 to both of these, so it is same as 2 comma 1. Okay. So basically 5 1 and 2 1, they are the correct pairs for A and B. And for B and C, 1 1 is correct pair. Right. So actually I can say that I have two correct pairs, 5 1 1 for A B and C. Like for A B C I have 5 1 1 and 2 1 1. They are the correct ones. Like I can simply multiply them. Like let's say hypothetically, I had that for my A comma B, I had this 2 1 pair and a 3 1 pair. and for B comma C, I had one 4 pair and one 5 pair. So for these indices, BI is less than CI, and for these indices, like AI is less than BI. Okay, so actually, I will have four answers. Like I can either have 214, 215, 314, and 315. Right. So actually, we can simply count for A and B के valid pairs and B and C के valid pairs and then just multiply them. So we will get A, B, and C के valid pairs where B is equal to 1. So we will multiply it by n in the end. So that's how we can move from n cube to n square. Like instead of iterating for one one jk, we will actually count um, I comma 1. Like this is for A, this is for B, and 1 comma j, that is B and C. Okay, so this will take O of n square because there's only one loop. There's only one loop for I, and check function is O of n. So O of n square will this will take, and O of n square this will take 1 comma j, and so we'll multiply them, and so it is O of n square only. Like you might not have understood this. If you have understood this, then let me know, and if you haven't, then also let me know. No. Okay, yeah, that one is fine. But basically, what I did was, I found the valid I for j equal to 1 and also the valid k for j equal to 1, right? And then I multiplied them together because I can take anyone from this and anyone from this. And then I multiply by n because j cannot be 1, it can be anything. Yeah, that is how I can put it very nicely, that I fix j equal to 1. Okay. And then for j equal to 1, I find the number of possible i's, and also for j equal to 1, I find the number of possible k's, right? And I can take any one of these and any one of these. So basically, the number of total I comma 1 comma j, I comma 1 comma k, that is just um, the product of these two, right? But j can be anything, not 1. So I'll multiply it by n. That is the answer. Okay. Okay, Surat. No, I equal to 1 will not work because like you are checking that for 1 comma j, like you are saying that I equal to 1. So are you saying that 1 comma j I'll count and 1 comma k I'll count and then multiply them together? Are you saying that? And then multiply by n? Like if you are saying that, then it is not correct because when you are counting for 1 comma j, you are checking that a should be less than b, and when you are counting for 1 comma k, you are checking that a should be less than c, right? So even if, like, it might be possible that even though a is less than b and a is less than c, but it might be possible that b is greater than equal to c, right? Like you don't know that a is less than b less than c. That is the thing. Like you can't really count 1 comma j and 1 comma k. You can count uh, I comma 1 and 1 comma k. Or like, yeah, if you are counting If you are counting 1 comma j and 1 comma k, where this 1 is for j, then also it is fine, because 1 comma j is same as I comma 1, right? Yeah, like to optimize O of n cube to, like, I initially told that any shift of a pair works, right? Like I explained that if you have a valid answer, then any shift of that works. So you can just fix any one of them and count it, and then you can multiply by n. Is this greedy? So greedy, like greedy means that you are making a choice at some point. There is no choice making here. You are just counting. So it is a counting problem, not a greedy. How much time I took in C? It was not very large. Uh, I guess 12 minutes for C. Wait, where did I go? There is some bug in this. Never mind. 12 minutes for C, I guess. Check my approach, please. So, what's your approach, Rishabh Patel? First, I'll show the code. Okay. Hmm. Okay. So I have a check function here, which takes in A and B, and the indexes where I want to check, where I want to start from. So I will iterate from, like, I equal to 0 to n minus 1. And if A of I plus j, like A of starting index plus I, is greater than equal to B of starting index plus I, so then I will return false. If for any of them it is greater than equal to, then I'll return false, else I'll return true. Okay. And in my main function, what I'll do is I will, this is for int j equal to 0, j less than n j plus plus. I check for, like, j comma 0. So I check for a b j 0 means I start with j for a and with 0 for b. Okay. And same for, like, b and c. I start with 0 for b and add j for c. And, like, I count the number of valid pairs in c1 and c2, and I print c1 into c2 into n. Okay. That is how you can do. Yeah. I mean, D was not very hard. I will explain and you will get. Each possible combinations of A and C, and I tried removing B's that results in incorrect using binary search. But, like, how will you do it in less than O of n? I don't think it is possible. Okay. So let's move to D now. A group of n people decided to decorate the Christmas tree. They have n plus 1 boxes of chocolates of decorations numbered from 0 to n. Initially, the ith box contains AI decorations. We said a permutation P of size n is fair if it is possible to hang all the decorations on the tree using the following process. Person P1 takes a decoration either from box 0 or from box P1 and hangs it on the tree. Person P2 takes a decoration either from box 0 or from P2 and hangs it on the tree, and so on. After person P1 follows and process repeats until all the decorations are on the tree. During this process, there should never be a time where person I needs to hang out decoration, but both box A and box I are empty. If it is cannot be avoided, the permutation is not fair. However, if the people can choose from which box to take a decoration during each step in such a way that this situation does not arise, then the permutation is fair. Calculate the number of fair permutations modulo this number. Okay. Yes, yes. And then I multiply them. Okay. So what D is saying is that we have some boxes, right? We have some boxes. We have n plus 1 boxes. Okay. So I have box number 0, box number 1, box number 2, box number 3, and box number 4. Okay. And basically, like I'll phrase the question in a different way. Okay. So, like, what we have is we have n plus 1 boxes, box 0, box 1, box 2, box 3, box 4. And, like, what they have said is that, okay, let's take this test case 61421. 61421. So, what they are saying is that we have to decide some order, right? Like we have to decide a permutation of length 4, P1, P2, P3, and P4. So we have to count such permutations. Like let's say one of the following permutation is 1342. Okay. So let's say this 1342 is the permutation. So what that means is that first the person 1 will go, like first the box 1 will be picked, then the box 3 will be picked, then box 4, and then box 2. And then again box 1, box 3, box 4, and box 2. Like what will happen each step is that uh, either we remove a chocolate from box 1, so it becomes 0, or we remove from this first, like 0th box, right? So, okay, let's say we want to check if this 1342 is fair or not. So, first we will like take from here, so it becomes 0. Then we will take from the third one, so it becomes 1. Then we'll take from fourth one, it becomes 0. Then we'll take from second one, it becomes 3, right? Then we take then we take again from 1, but it doesn't have anything, so we will take from the 0th one, so it becomes 5. Then we will take from third one, it will become 0. Then we will take from second one, sorry, fourth one, and it doesn't have anything, it has 0, so we will take from here, and then we will take from second one, so it becomes 2, right? Then again we come to 1, it has 0, so we will take from this thing. Then we will come to 3, it has 0, so we will decrease from here, 2. Then again 4 has nothing, so we will decrease here. And then we come to 2, so 2 becomes 1, right? Then again we have with 1, so 1 has nothing, we will decrease here. Then we go to 3, right? So 3 has nothing, right? But now also this one also has nothing, 0 also has nothing, so we have to stop here. Like we cannot really do anything now, so we have to stop here. And since this one is still remaining here, so this is not fair, like this permutation is not good. Okay, so we won't count it in our answer. Okay, that is the thing. So that is how we are trying to do. Like we are deciding an order. We are deciding an order for this, like the order in which we take, right? And we want to count the number of valid orders. Like there are order n factorial. No? There are n factorial orders, so we have to count the number of valid ones. So actually, to rephrase this, like initially it was 61421, right? 61421. So actually, instead of counting the rearrangements, like instead of counting the number of permutations, like 1342 is a permutation, then maybe 14 2, 3 is a permutation, right? So instead of counting number of these, actually what I can say is I can arbitrarily rearrange this. Like let's say I can rearrange this from A1 to AN. Like I can make it anything. I can make it 1 4 1 2, or I can make it 1 4 like 1 1 1 1 2 4, right? And basically after rearranging it, I will go from left to right. Like I will remove from here, then from here, then from here, then from here, then again from here, from here, from here, from here, then from here, and so on. Okay, so instead of making a permutation like p1 up to pn, I'll count the number of rearrangements in this. Like I have basically rephrased the question that if we can rearrange the a1 to an, then you have to count the number of rearrangements such that we can empty all of them. If we go from 1 to 4, so 1 2 3 4 1 2 3 4, if we do like that, then in how many rearrangements can we empty the entire thing? So that is what we are looking for. Like that is what we have to solve. Okay. So do you understand how I changed the question and why it is the same? Ayush, conclusion for D. I will explain. Then you will understand. I don't get your comment. So do you guys get what I have done? Like instead of counting the number of permutations, that is P1, P2, P3, P4, what I am saying is we can rearrange the elements from A1 to A4 in any way we want, right? And we have to, like after that we have to move from left to right. 1 2 3 4 1 2 3 4, and in such a way that finally all the numbers are um, exhausted, right? So we have to count the number of rearrangements. Okay. Yeah, so you guys understand that what is the um, new problem, right? So for example, this 1124, 1124 might be valid. um, okay, like let's try if 1124 is valid or not. So first I will look at this one, so I'll take from here, then I'll look at this, so I'll take from here, it becomes 0, this becomes 1, this becomes 3, right? Then I have 0 here, so I'll take from here, so it is 5, then I have 0, so it becomes 4, then this becomes 0, this becomes 2, then this is 0, so I'll take from here, so it becomes 3, so this is 0, it becomes 2, this is 0, it becomes 1, and this will become 1. Okay, and now again um, I can't like take from here, so it will become 0, and then I can't take from here as well, right? That's where we are stuck. Okay, so this is why, like, that initial thing that we started with 1124, uh, if you can see 1124, this is not valid. Okay, so we won't count it. So now we basically need to ask ourselves that given this A0, A1, A2 up to AN, we need to count the number of arrangements such that um, we can like empty out the whole thing if we go from left to right. A1, A2, A3 up to AN, again A1, A2, A3 up to AN, and so on until everything is gone, right? So actually what you can again think of it as one more thing, like you can think of this problem as like, okay, let's just count how many times we go through the array. Like let's say if the total sum of my elements, if my total sum, like I'll take an example, I'll take this example only, that 61124, right? So we have 61124. So what we have is that the total sum of these elements is what, like 6 plus 1 plus 1 8 plus 2 10 plus 4 14. So we have 14 elements, right? And on each step, on each step we are decreasing one element, like either from here or from the index, right? So at each step we are decreasing by -1. So the sum will decrease by -1. So we have to perform at the 14 steps, right? We have to perform 14 steps. That is the thing. So like if I am doing this 14 times, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, right? So basically, I will be visiting this index 1 4 times, this index 2 4 times, index 3 3 times, and index 4 3 times, right? So essentially, I want to have that, like the numbers here must be sufficient, right? Like I visit this index 4 times, but I have only one here. Like you can see that I visit this one 4 times, this one 4 times, this one 3 times, and this one 3 times. So even though I visit this like 4 times, I only have one here. So actually, the next 3 times that I visit, like if I want to complete the entire thing, the next 3 times that I visit, I will have to take from here. So I will have to take 3 from here, right, to make this 4. And again, this one also, I'll have to make 4. So I'll have to take 3 from here. So it becomes 0. But now this index, this also needs 3. It needs 3, but it has 2 only. So, and this is empty now. So we cannot really give it to this, right? And that is why this 1124 does not work. Like that is why this 61124, it is not good. Like we cannot really go from left to right and empty out this. And actually, the main reason here is that if we go like this, 1 2 3 4 1 2 3 4 1 2 3 4 and 1 2, then we are visiting this last element only 3 times, right? But the last element has 4. So like it has one extra. Okay, this 4 is something extra. So we cannot really distribute this 6 into these such that all of them get what they want. Like finally our goal is that these numbers should become these numbers, and we can distribute this 6 among these numbers, right? Like we can distribute this 6 among these 4 numbers such that all of these final numbers become these, right? So the sum is consistent. Like the total sum of these 5 numbers is 14, and this is also 14. That is fine. So that is one condition. But the thing is that we cannot subtract from any of the numbers. Like we can only add to it, right? We can only add to it like this. We cannot take away from it, right? So if any number is greater than what it needs to be, then it is not possible, right? So like if I have 4 somewhere else, like let's say if I have 4 here and I had 1 here, then if you see, all the elements are less than equal to their value, like this value, right? So like I can actually transfer 6 very easily. Like this will gain 3 from here, this 2 will get 1 from here, and this 1 will get remaining 2 from here, right? And in this way, finally it will become 4433, right? And so it will work like 1 2 3 4 5 6 7 8 9 10 11 12 and 13 14, and now we have emptied the entire thing, right? So based on the sum, like since the sum was 14, so we knew that what is the final value that we need to make on each index, right? So like if I give you one more array, let's say 8 1 2 5 4. Okay, so if I ask you that, is this array, like if I do the process, then will this array empty or not, right? So what we'll do is we'll first find the sum. So sum is 9 11 16 and 20, right? And so 20 by 4, like we will have to visit every element 5 times. So 5 5 5 and 5, So like you can see that all of these elements are less than 5. So we can empty this out using the process, right? Because I can distribute this 8. I can distribute this 8 in such a way that everything becomes 5, right? So the entire condition is that my a1 to an values have some limit. Like I can calculate, like I can find the sum. I can find the sum from a0 to an, and based on that, I can calculate the limits on each element, that I want each element to be less than that bi, less than, sorry, to be less than that bi. Okay, so I can calculate these values, and then what I have to do is I have to count the number of permutations such that all of these arrays, like all of these array values, are less than the bi values, right? So the only condition is that every ai should be less than equal to every bi, right? If any one of them is larger, then we cannot empty that array. Okay, so do you get till here? No, some parts will also work, right? Because in the process, you can take one also from that. Like when you are visiting, let's say 6 1 4 2 1. Let's say you have this. Okay, so like when you are visiting it, you are here, so you make this 0, then you make this one 3, then this 1, then this 2 0, then you came here, then you come here. So since you cannot take from this, so you will take from here, you will make this 5. So like you have taken 1 from here, right? So um, you are like you can take partially as well. Like the final condition is that the array elements from a1 to an must be less than equal to some value bi. Okay, how to find this bi, I'll tell you. But okay, so do you guys understand this? That every element, the only condition is that every element should be less than equal to that limit. Okay, so macdon, do you get it? Okay, let's assume he gets it. Okay, so yeah. So now what is the value of bi actually? Let's find it formally. Like let's say uh, you have this 0 1 to n, right? 0 1 2 3 up to n, and let's say the sum is s. Sum is s. So you are going like this: 1 2 3 4 5 6. Again 1 2 3 4 5 6. So like in one cycle you are performing n sum, right? Like in one cycle you are decreasing sum by n. So like uh, s by n, these full cycles you will need. Like let's say if your sum is 13 and your n is 4, sum is 13 and n is 4, right? Then first of all you will do 3 full cycles, because 13 by 4 is 3, right? So 3 full cycles, right? But then, so you have completed 12, right? But one is still remaining. So you will again visit this one again. Okay, so like everything else you will visit 3 times. Like you will visit everything 3 times. That is n s by n times, s by n times, and so on, s by n. But this first, like, then again you will visit some part of cycle one more time, right? So it will be plus one, plus one. Okay, like plus one only for the first value which is remaining. Like if you are doing s by n, then the remainder, which is S mod n, they are remaining, right? Let's say like in 13 and 4, if you do 3 full cycles, then 13 mod 4, which is 13, the remainder of 13 if I divide by 4, which is 1. So 13 mod 4, 1 is remaining. So again, you will go back for one element, right? So basically, what I can say is that the first S mod n elements, the first S mod n elements would be n by s plus 1, and the rest of them would be n by s, right? So I want that my array should be rearranged in such a way that every element is less than these quantities. Okay. Yeah, exactly. So now I want to count the number of permutations such that every element is less than this value or this value wherever, depending on where they are. Like if they are in these positions, then they have to be less than equal to this value, and if they are in these positions, it has to be less than equal to this value. So we have to count the number of rearrangements, right? So now how to count that? Like your problem just becomes that given an array A and an array B also, find the number of permutations, number of arrangements, number of arrangements of array A such that AI is less than equal to BA for all I, right? That is what your question has become, right? And this can be solved by simple PNC. Okay. So I will take an example to like explain this. So let's say we have like A naught, A1, A2, A3, and A4. Okay, so let's say we have um, 10, 2, 3, and 4 and 5. Okay, so first of all, we find the sum. Like first, we find the BI values, right? So the sum is what? 2, 3, 4, 5 is 14, and plus 10. Okay, it is not a good example because multiple of 4 are added. So let us decrease this 10 with 10 to 8. Okay, so this is 8. So 10 plus 3, 13 plus 4, 17 plus 5, 22. 22, right? Okay, 22 is still not a good example. So I will change this 8 to a 4. So we'll get 18. Okay, 18 we will get. So we will have 5, 5, and 4, 4. Right? We have these limits 5, 5, 4, 4, and we have to like count the number of rearrangements of this array. Okay, such that a1 is less than or equal to 5, a2 is less than equal to 5, a3 is less than equal to 4, and a4 less than equal to 4. Okay, so let us try to build that. Like let's say we want to build a 4 element array such that this a1 must be less than equal to 5, a2 must be less than equal to 5, a3 must be less than equal to 4, and a4 must be less than equal to 4. Okay, so actually what we can do is basically we want to put these 4 elements, right? Like in our bag we have 4 elements, 2, 3, 4, and 5. This is our bag, and we have these 4 elements, 2, 3, 4, and 5, and we want to put them uh, inside this array, right? So actually what I can do is I can start from the biggest element. Okay, let's say I start from this 5, right? So for this 5, how many options do I have? Okay, n by s. Sorry, I guess I wrote, yeah, sorry, s by n. You get my point. All right. So what I was saying is if we want to rearrange this 2, 3, 4, 5, like I want to put these 2, 3, 4, 5 into these into these four blanks. So I want to find the number of different possible ways, number of different ways. So for the 5, like where can I put 5? Where can I put 5? That's my question. So actually I have two possible positions for that, right? Either this one or this one. Either this one or this one. Okay. So I can put 5 into two positions, right? Then where can I put 4? Where can I put 4? So actually I have all the options. I have four options, but actually um, I have only three because the place where I have put 5, I can't put 4 there. Okay. So for 4, I have three options. Then for 3, like 3 also I can put anywhere, but I have already put 5 and 4. So I cannot put 5 and 4 there. Like I cannot put 3 at the positions where I have put 5 and 4. So 4 minus 2, which is 2. So for 3, I have two options. And then for the remaining 2, I have only one option. Right? So I'll multiply these 2, 3, 2, and 1. So which is 12. Okay. So this is how you solve it. Okay. That you start from the highest value. And why we start from the highest value? That is also one question. Actually, if you start from the lowest value, like the thing is that, see, what I did here was I first put 5 in some of these, like either this one or this one, right? Then I put 4, and I saw that I can put 4 in 4 different blanks, but I already put 5, so I did minus 1, because I know that wherever I can put a 5, I can put a 4 also, because if 5 can be put somewhere, that is, if the limit was less than equal to a and 5 is less than equal to that a, then of course 4 also is less than equal to that a. So everywhere I can put 5. That is the observation. Everywhere, everywhere I can put 5. I can put 4 as well. So actually, it doesn't matter where I put 5. Like I can put 5 anywhere out of these two positions. And for 4, I will definitely have three possibilities, because either I put 5 here or I put 5 here, and in both the cases I will have three options. I have three options for the 4, right? And similarly for 3, for 3 also, I can put this 5 and 4, like wherever I can put this 5 and 4, I can put 3 also. So like if I say that I can put 3 at 4 positions, उसमें 5 and 4 वाले भी आ जाएंगे. Like 5 and 4 also must have been put in that position only. So I'll have to decrease minus 2. So for minus 2, which is 2. Okay. That is how you can solve this. Like if I give one more example, let's say if my array A is something 1, 2, 3, 9, 5. Okay. And array B is 2, 4, 6, 7, 10. Okay. So what I'm saying is start from the highest. Like I have these blanks, right? In the first element I want 2, then I want 4, I want 6, then I want 7, then I want 10. So what I'm saying is start from highest. Okay. So for this 9, you have only one option. 9, right? Then for this 5, okay, so I will multiply by 1. So like, see, so for 9, you have one option. Then for this 5, you will have like these three options, right? 6, 7, and 10. But 9 is definitely in one of these. Like actually 9 is here only. So 9 is in one of these. So essentially you have two options. So for 5, you have two options. Then similarly for 3 you had four options, right? But you already have two elements sitting in those. So for 3, essentially you have only two options. Then for this 2, you have all the options, but three numbers already there. So you have 5 minus 3, which is two options for 2. And for the 1, you have all the options in the world. Sorry, not 1. For yeah, for 1, you have all 5 options, but 4 are already there. So for 1, you have only one option. So for this, the answer is 8. Okay. You can just do KCR into n minus r factorial, where k is equal to number of elements less than equal to the floor of s by n, r equals to n minus s mod n. So what you do is you choose. Okay. Yeah, I think that also works. Like basically, you will first check that all the elements are less than equal to that higher value. Yeah, like you are exploiting that we have only two values right here. You are exploiting the fact that we have s by n plus 1 and s by n only. So what you are saying is, let's say um, this is r. Like r is the number of s by n's, and this is n minus r, the number of s by n plus ones. So what you are saying is, if any element is greater than equal to, if it is greater than s by n plus 1, then the answer is 0, right? Otherwise, um, you will have to put s by n plus 1. Like if there are any elements which are s by n plus 1, you will have to put them here, right? And the remaining k elements, you can choose any r of them and put them here, right? And then you can rearrange them. Like you can rearrange n minus r factorial and r factorial. That is also correct. So that is also correct, and it is, I guess, simpler also. So nice. This is also a nice solution. So do you guys get this problem? Like get his solution also and mine also. And so here k has to be less than sorry, greater than equal to r. This is correct. So do you guys get this solution? Like both solution actually. Okay. So I'll show the code for my solution. So we have int n c in n, val equals to 0. So this val is the first element. Okay. And then I have n length array, which is a. So I see in ai. Then I find the sum value, like the sum. Then s by n I store in low variable. S by n plus 1 I store in high. And number of highs is some mod n, and number of lows is n minus some mod n. Right. So these four variables I just store, and I have this answer. So since I am multiplying some terms, so answer start with 1, the empty product. Okay. So then I sort this array in decreasing order. Okay. So I start from the highest number first. Now I will iterate over this array, like what I did here. That I iterated over this array. That is, first I look at this 5, then 4, then 3, then 2. Right. So for the 5, I calculate the answer, which is num high minus I. Like basically, this is overkill actually. That is right. Like if AI is greater than high, that is if any element is greater than this high value, then of course the answer is 0. So I just print 0 and return. Then if AI is greater than low, that is it is equal to s by n plus 1, then I have only num high minus 1 minus I options. Like until now, uh, I indices have been placed. So and total was num high, right? So num high minus I, that is the thing for this one. And if AI is less than low, I mean less than equal to low, that is it is less than s by n plus 1. So we can put it anywhere. Okay. So since I are used up, we can put at anywhere. So n minus I, right? And then I do this for like num high to n. Like first I just do this for num high variables that um, they must be at most high minus 1, right? If it is at least, so they must be at most high. So if they are more than that, then I'll break. And then like I'll explain this code, like there's no purpose in explaining it, because you can simply do kcr into n minus r factorial into r factorial. That is like you can always do this, but what I wrote I'll just explain. Like let's say you have 4 4 4 3 3 3, right? So let's say my array is 1 2 2 2 4 4. Okay, so I reverse sort this. If I reverse sort it, I get 4 4 2 2 2 1. So what I did was first I iterated from 1 2 3. Like I just checked these three elements, and they must be less than equal to high, right? Then only I can put them. Okay, and if it is less than high, then I can put this anywhere actually. Like if it is equal to 4, then I can put them on these three, and if it is less than 4, then I can put them anywhere, right? So I just did that, and then I checked from here that they all must be less than equal to this 3. I cannot have 4 here. Like let's say if I have 4 4 4 4 2 2, then the answer is 0, because I have a 4 here, but I cannot put it. Okay, so I did this. Like the code is not very good. It is complicated and unnecessarily, but yeah, it works. So this is the code for D. Can't E. What do you mean can't E? Let's move to E, I guess. So E was called New Year's gift. Monocarp has n friends and decided to give a New Year's gift to each of them. He also has prepared M boxes to place the gifts in. The beauty of the ith box is AI. Every box can contain at most one gift. Monocarp wants to give gift worth at least YI coins to the ith friend. Additionally, he knows that the ith friend will be happy if at least one of the following conditions holds. The gift is in a box with beauty at least XI, and the gift, like, or the gift is worth at least ZI, where ZI is greater than YI. Your task is to help Monocarp calculate the maximum possible number of friends he can make happy if he has K coins. Note that Monocarp must purchase a gift for each friend, and the gift may not necessarily come in a box. I guess you can do that. Like the implementation is up to you. I just told the logic. Like you have to the condition I just told you, and you can implement it however you want. You can use PNC or you can use like code or some whatever you want to do. Okay, so what we have here is um, yeah, that we have n friends. Okay, we have n friends, and we want to give them something. Okay, so for the ith friend, like okay, these n friends are of different value to us. Okay, some are close, some are not. So for the ith friend, we want to give them at least yi. We want to give them a gift of at least cost yi. Okay. So even though gifts should not be measured by their cost, they are doing that right now. So we will play along with that. So we want to ensure that the gift that we give to the ith person at least has cost yi, right? But actually, our friend is greedy. So if I give him the gift of yi cost, he won't be happy. Instead, what he wants is at least zi cost, where zi is greater than yi. Like according to me, I want to give him at least 4, but he will be happy only if he gets at least a 6 cost gift. Okay, so either he gets a 6 cost gift or he gets a box. He gets a box of at least xi beauty. Okay, so basically, I have some boxes also in which I can place the gifts, and they are of different beauties. Like the ith box is of gift AI, is of beauty AI, right? So either I can give the friend at least 6 cost value, like either 6 cost gift, or I can give it in a box having at least xi beauty. Okay, and in these cases, that friend would be happy. Okay, so we want, like, we are a people pleaser and we want to maximize the number of friends that we make happy. And we have K coins in our bank account and we can spend all of it to please people. Okay. So I have to find out that what is the maximum number of friends that we can have, that we can make happy actually. Okay. So how do we solve this? Like first of all, you can see that if I have n friends, if I have n friends, and like I want to give the ith of them at least yi coins ka gift, right? Then like basically this yi is fixed, right? Like if I have k coins, and to the ith friend I am gifting yi always, then actually I can just get rid of it, right? Like I can assume that I have k minus summation of yi coins, and I have now purchased a gift for at least yi coins for each one. Like essentially, I have k minus summation yi coins, and um, my friend would be happy if I give him zi minus yi coins more. Like see, um, I have in this test case I have two friends. So we have x, y, z. So for the first friend, x is 1, y is 2, z is 3. And for second friend, x is 1, y is 2, z is 7. And we have 6 coins. So basically, the thing is that first friend, we want to give both friends a gift of at least 2, right? So essentially, our 2 coins are gone, at least 2 coins, or like 4 coins are gone already. So essentially, we have only 2 coins left. We have only 2 coins left, and we can say that we have to give them at least 2 coin gift, right? So if we give them 1 coin extra, like let's say if I write the value of z minus y here, so this is 1, this is 4, right? So if I give a friend 1 coin extra, then he will be happy, right? And if I give a friend 4 coins extra, then he will be happy. Okay. So like if I ignore the boxes, then I can make only this friend happy because I have only 2 coins, right? So my point is that either give them a gift with the box, sorry, either give them a box and they will be happy, or give them extra z minus y coins and they will be happy, right? But you have only 2 coins left and you can give only him, so you can make him happy like that. And also you have boxes, right? You have 3 box, you have a box as well. Like you have this one box, you have a box of beauty 1 as well. So you can give this box to the second friend, and since its x value is 1 and the box value is greater than equal to x value, so he will be happy, and that's how both can be happy. So basically what I am saying is that we can simply do k minus equals to summation yi and set all the zi to zi minus yi. That is, we want to give this much extra to a friend to make him happy. Okay, like yi is on दे ही रहे हैं, but this much extra we'll have to give to make them happy. And so effectively our coins is k minus summation of yi. Okay, so do you guys get till here that to make him happy, to make them happy, either give them either give them extra zi minus yi coins, right, or give them a box of at least xi beauty. Okay, that is the thing. So do you guys get till here? How I boiled on the problem? Like the problem initially said that we want to uh, make the gift at least z. Like, do you guys get the problem? The reduced problem. Like why I did k minus equals sum of yi and z minus equals to yi. Like, do you guys get these two statements? Okay. So basically, I have a new value of zi now and a value xi in my problem. That is, either I can give the ith friend a box of xi value, or I can give him zi coins, right? But in total, I have only k coins. Okay. So I want to maximize the number of friends that are being happy. And like I have some m boxes, right? A1, A2, up to am. I have these m boxes. So like um, now the thing is that you can see that the boxes don't cost anything, right? Like these boxes actually don't really cost us anything. We can give them away for free. The only thing that costs us is zi. Like if I give zi to a friend, I have only total k, so that is restricted. But these boxes I already have made, so I can give them all away and it doesn't really matter, right? So best would be to just give most of them away, so that I can, like, to the other persons I can give zi money, so that um, my coins would not go so much. Like I want to maximize the number of people to make happy, right? So for example, if I have three boxes of 3, 4, 5, okay, and I have three friends. One friend, the value of xi and value of z minus y. So the value of x for this friend, let's say, is 6, and z minus 5 is 2. And let's say I have 10 money. And let's say for this friend, the value of x is 4, and z minus 5 is 10. And for this friend, I have the value of x is 7, and z minus y is 3. Okay. So like either I can give this one friend 10 coins, right? And so one friend would be satisfied. They would be happy. Or actually what I can do is I can give this friend a box of beauty 4. So he is now happy, and I can give these two friends 2 and 3 coins each. So I'll still be left with 5 coins, and these two would be happy. So I can make these three friends happy like that. So like I can give the boxes to anyone who I like, and they will be happy. Given that this value is less than that, like given that this xi value is less than equal to that aj value, right? So now we want to give the gifts in such a way that the remaining values are minimized. Like basically, let's say if I have some n friends, right? I have friend 1, friend 2, friend 3 up to friend n, right? And um, yeah, and like I have m boxes 1, 2, 3 up to m, and each friend is an xi value and a zi minus yi value. So I'll call this value ti. Okay. So extra money is ti. So what I want to do is I want to distribute this m boxes into the n friends such that, like, okay, let's say I give the box number 1 to person number 2. I give box number 2 to person number 4, let's say. And like basically I just eliminate some persons. So the remaining friends I have, like for the remaining friends, I will give them money, right? I'll give them TI money, and I want to maximize the number of people that I can give money. So preferably, I want to like I want to minimize, like I want to make sure that the TI value, the TI value of remaining friends, of the remaining friends is as low as possible. Like basically, I want to eliminate the high TI values using the gifts. I mean, using the boxes, and then the smaller TI value I can give using my coins. Right, that is my strategy. So, like, let's say we have three gifts, 3, 4, and 5, and we have three friends. Um, or let's say we have five friends. Okay, so 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. Okay, so these are the five friends that we have. This is the xi value, this is the ti value, right? So what I told you is that we will gift these boxes to the highest ti friends, so that, like, let's say we give these three boxes to these three friends, so that we'll only have to spend 5 coins to satisfy these, right? Or like if we have only 2 coins, let's say if we have only 2 coins, then we can just give this one, and this friend will remain unsatisfied, right? But instead, if we had given the three boxes to these three people, let's say, okay, then the three would satisfy. But then if we have only 2 coins, then we can't really give to these two. Like then the answer would just be three. Otherwise, if we give 3 coins to three boxes to these three, then the answer is four. So definitely, it is more optimal to give the boxes to the people higher TI value. But now the thing is that this X is also there, right? Like not everyone is suited with all types of boxes. Like let's say if I have some boxes, 1, 2, 3, 4, 5, 7, right? Then not everyone wants every box. Like let's say I have three friends. One is 5 comma 10, one is 7 comma 11, and one is let's say again 5 comma 13, right? So even though I have like 6 boxes, but this friend only wants either this or this box, this friend only wants this box, and this friend also only wants either this or this box. So actually none of them want these 4 boxes. So basically they are waste, right? So like what can we do now? Like how do we distribute the boxes so that the remaining cost is minimized? So what we can do is we can start with the highest value box. Like see the idea that I told here. What did I tell you here? That let's say, yeah, we had this example, right, where I wanted to place 1, 2, 3, 9, and 5. into these spaces such that every AI is less than equal to every BI, right? So I told you that wherever 9 can come, there 5 can also come, right? So like 9 can come here, so 5 can also come here, and that's why we can do um, like 3 minus 1, that these 3 minus 1 where 9 is put. So basically, since 9 is greater than 5, wherever 9 can come, 5 can also come. So the same idea we can apply here, that if I look at this gift, like if I look at the gift number 7, so let's say I want to give this out. So of course, okay, the thing is that all the gifts, they are free, right? They are of zero cost. I can give them out for free. So of course I want to give them all out. Like I want to give all of them out. So what will I start with? I'll start with the highest gift first. Why? Because um, if I start with a lower gift, like let's say I start with 1, so a person which can take 1 will take 7 also. Like he will take 7 as well, but the reverse is not true. Like I'll make an example. Let's say we have, okay, let's say we have 7 and a 10, and we have a 1 and, like let's say, a 9, or let's say 1 and 11. Okay, so it's like, okay, let's say we have these two friends, and we have only two gifts, right? Like sorry, we have only two boxes, 1 and 7, right? So we have two boxes, 1 and 7, and we have two friends. One is 710 and one is 111. So like the point is that this 7 man will happily take this 7 only, not this one. But this one man will take either of them, right? So like if I talk from the box's perspective, this 7 can be taken by either of these, right? But this one will only be taken by this person right here, right? So like if I start from the highest one, like if I take this 7, like if I start from here and I see that which person has the highest xi value. Like what I want to do is I want to minimize xi, right? I mean ti. I want to minimize ti values. See, this is x value, this is t value, and I want to like distribute the gifts in such a way such that this t value of the remaining people is minimized, right? That is, I want the higher t value people to be gone. I want to give them the boxes. So if I have these two boxes, 1 7, and I start with 7 first, then I give this 7 box to someone. So this person also will take that on, and this one will also take that. So whom should I give to? So I will give to T, like the higher one, right? So I will give this one to this person, right? So 11 is gone. Then I will look at this figure, and I can't give it to him, right? Because he has higher standards. So like now I'm left stuck. I cannot give this one, and so this 10 is remaining. So I have to spend 10 coins, right? But instead, if I had started with a lower number, like instead, here I started with 7, right? But if I started with 1, okay, like I saw the 1, and I just checked that which people are able to take this gift. So only this person is available to take that gift. So I give it to him, and this is gone. And then I look at this 7, and I can give 7 to him. So this is also gone, and so I'm able to get away with zero cost. Okay. So my point is that you can process the gifts in increasing order. process the what boxes in increasing order, increasing order of AI, and like remove the highest, like give it to the highest TI value. Okay, that's the entire point. Like this is the algorithm that you can process the boxes in increasing order of AI and give that box to the highest TI value for that, like AI. Like whoever is willing to take that box, you will give it to the highest TI value holder, so that you have the minimum remaining, right? So do you understand this? Like I'll show it in example as well. Let's say the examples are pretty bad, to be honest. Let me open this submission. Okay, so let's say we have this example, or we have this example. We have, okay, n is 1. Let's take something better. 2, 7, 15. Okay, this one. So for this example, we have like 7 boxes, right? We have 7 boxes. Yeah, 7 boxes, and we have 2 friends. So TI value is 2 for this one, and XI is 5. And for this friend, the TI is also 2, and XI is 5. And coins are 15. So this is also a not very good case. But anyways, so we will start with the lowest box, 3. So who can take it? No one can take it. Okay. Then we'll start with 5. So who can take this 5? Both of them can take this 5. So we'll give it to the lower TI value, and both of them same TI value. So we will just give it to him. Then we look at this 5 box, and he can take it. So we will give it to him, and this is gone. So both are satisfied. The answer is 2. Like the sample is not very good, but you get my point, right? That just start from the smaller box, because someone who can buy the smaller box can buy the higher one as well. Like someone who is happy with the smaller one will be happy also if we give the bigger one. So we'll start a smaller one only, and just give it to the highest TI value. Can we binary search to find the app value for the of the box for the person? No, like actually, it might happen that for multiple people, the apt value can be the same. Like it might happen that the same box comes out to be the optimal value for multiple different people. So who will you give the box to? So any doubts? Any more doubts in this? Or if you want me to repeat any part? Uh, like basically the point is that we want to minimize the cost, right? Like the boxes are saviors. Like the boxes don't cost us anything, and they eliminate one person, right? And also, um, we want to minimize the cost of the remaining persons. So we'll try to give the boxes to the highest TI value, but not every person will accept every box. So I just started out with the least popular boxes and gave it to anyone wants to have it, right? That is the kind of intuition. And actually, during the contest, I misread the problem. Like I thought that the boxes also cost. That if a box has beauty AI, then it costs us AI coins. I thought that, and I was trying to solve that, and that is not possible to solve. Like at least I could not solve it. So yeah, like in the last 10 minutes, I um, read that these boxes do not cost anything, and so I submitted that after just of the contest. Like I was at this page at submit code, I pasted it, and I clicked this button, submit button, and just 0.1 seconds before that, the contest got over. But yeah, that's my bad. I did not read it correctly. No, like if you can see, um, I was trying E only, and I submitted E very late. Like, in fact, yeah, I told this. I did not try F. Okay. How did D get 4K solves? Like, it is pretty standard actually. On CodeChef as well, this problem has appeared sometimes where we want to ensure that AI is less than equal to BI. We want to count the number of arrangements of AI such that it is less than equal to BI. Like, this problem is standard, but reaching to this problem, that was like, it was not very tough to be honest. But maybe AI could have AI was able to solve it. Maybe I don't know. Should we try? I guess if I open ChatGPT, you will see my chats. So I won't do that. That's also good. Okay, I'll try it. I'll solve it because some of my friends have solved it. So I will try to solve it as well. Thanks. Anyways, let us end this now. If there are no doubts, and not now. I'll try it later. I'll absolve it. Yes, I know the PNC question. Like I told you that the condition for an array to be valid was that at every index it should be less than 5, less than 5, less than 4, less than 4, right? So to count the number of permutations of that, that is a standard problem. I don't think so, man. Like I'm not that skilled that I would solve it in any reasonable amount of time. I mean, okay, I don't know what's your point, but good for you if you solved it yourself. All right, so let's end this now. Thank you for joining in. I hope you understood. I will see you guys later. Bye bye.